We are 6:03. So let us start our today's session on this virtual conference series. So we are entering into our almost third talk of the series in advances in 2D quantum materials. And today's talk is a special talk because our speaker, Professor Arindam Ghosh, has been recently awarded with the Infosys Science Prize. And I think it's a great service in terms of his tireless effort contributing to the experimental condensed program in the country. And so he's going to talk about his core research area in graphene, and especially going to give us about the recent magic spells in twisted bilayer graphene. So with this introduction, let me again mention that if anyone who wishes to raise questions during the session is free to do so. They can unmute their microphone and raise the question anytime, or you could raise this on the chat box, and we can take those questions maybe during the talk or at the end of the talk. And I would request everyone to stay muted so that there is no interruption during the talk. So with this, let me pass on the microphone to Arindam. And Arindam, it's a great pleasure to have you and to listen to you forward to this wonderful talk.
Good. Thank you. Can you hear me, Karthik?
Yes, and I'm going to turn off your video as well so that we save on the bandwidth.
Yeah, shall I? Oh, I can turn off my, or you will turn it off, right?
Yeah.
Okay, good. Okay. First of all, thank you, Karthik and Dhavala, for this invitation. As I was mentioning, I wanted to visit TIFR Hyderabad for a while, but it didn't happen. But at least electronically will be a good idea. So I'm going to be talking about bilayer graphene, the twisted bilayer graphene, which has been one of the major group activity in my group here. We work on various kinds of twisted 2D systems now, given the kind of interest, global interest that has started in this direction. And optoelectronics is one of the directions, but another major direction is looking at the thermoelectric properties of this system. We have been trying to see if thermoelectricity can be used not as just a interesting physical property to measure or a characterization, but whether the thermoelectricity can be used to get fundamental properties investigated. So that's the reason. Okay. Right. So before we get started, let me just acknowledge the people who have been involved in it. These 5 people on the left are actively working in various aspects of twisted bilayer graphene. Fani has finished PhD, Bhaskar and Aditya just finished, Bhaskar will be finishing, and Manjari is the postdoc, and Sheshav just joined the group. My colleagues who have been doing the theoretical as well as experimental contribution to this are on the right. It is Shubhrata Mukherjee, H.R. Krishnamurthy, Manish Jain, Chandni, Tanmay, Sumilan. They are all have contributed in some way or the other, and we are continuing these collaborations. Most of the papers either are published or on archive for you to take a look. Right, so the twisted bilayer graphene itself is not a stranger anymore. When you have 2 layers of graphene on top of each other, which slight angle between them, then you get what you call a Moire lattice. And usually the Moire lattice, as you can see in my pointer, is much larger than the real lattice of graphene itself. And as a result, the Brillouin zone of the Moire lattice is much smaller. Now, once you have this small Brillouin zone, the original bands starts getting folded, which leads to a very different type of electronic spectrum in twisted bilayer graphene than the original host single layer graphene or even bilayer graphene itself. Okay. To give you a big idea, this was old calculational work, and you see that when you have a large angle between two graphene layers, when it's on top of each other, you retain the conical band structure over here. Whereas when you have a angle which is close to a degree or 1.5 degree or so, you get this folding of the band, and the repulsion flattens these bands, and which is why it's so very interesting. So two different regimes. First regime is large angle, where the linear dispersion is maintained in the two layers, and the two graphene layers behave essentially in a decoupled manner. That means they are essentially independent of each other. Whereas if you go to these lower angles, because of the flatness of the band, electronic bands, you have probably the electron-electron interaction becomes very strong, and there is a growing school of thought that strong correlation physics can be obtained, and that led to various kinds of discoveries in superconductivity, spin-Hall ferromagnetism, and so on and so forth. But it is not the only story. The electronic physics is not the only story. It's also very interesting when it comes to the hybridization of the lattices. Now, if you see the two graphene layers, which are separated by just about 0.3 nanometer, you see the out-of-plane vibrations of the two layers, they start hybridizing, and a whole new phonon modes appear. So you can see the ZO phonon mode, which is denoted by this line here, and this essentially is a quasi-optical line, because at zero wave vector there's a finite energy. But this is a result of the hybridization of the two layers, which are out of plane vibration, but it's it's called breathing mode. And this has energy of approximately 100K, or these are the ZO modes, which are 100 centimeter inverse, which is roughly about 100 Kelvin energy itself. Okay, so there are two different phenomena that occur: the electrons hybridize as well as phonons. Electrons, of course, hybridize at a much lower angle. Phonons hybridize almost at a much wider range of angles. So the question in these twisted bilayer graphene, what are the possible phenomena? First of all, the question is the nature of the interlayer coupling itself. That means, what is the energy scales as well as other properties between the two layers, and that requires understanding of the cross-plane thermoelectric properties or transport properties in general. Whereas if you want to know the nature of electronic states or the strong correlation effect in this twisted bilayer graphene, which is these two, then you want to look at properties which are within the plane, or in plane transport and thermoelectric properties. Okay? So what I'm going to show you today is both these different ranges or types of measurements. One will be out of plane thermoelectric properties, other will be in plane thermoelectric properties. Right. So just before going into the thermoelectricity, let me just tell you why is it interesting to us. To give a very small primer on this, you know what thermoelectricity is. If you have a solid and you want to create a temperature difference, it leads to a voltage difference as well, because because the electrons essentially travel from the hot end to the cooler end, and in the process it suffers collision that leads to a potential difference. Okay? There are two different types of collision that is important, and this is called, one is called this diffusion thermopower, and diffusion thermopower is given by the semi-classical Boltzmann equation, where all these energy cumulants of scattering time comes into play. But interestingly, when you combine these parameters, you come to an expression for the thermopower, which is extremely powerful and has been there very robust in large number of metallic and semiconducting systems. where you see the thermopower is essentially proportional to the derivative of the logarithm of conductance G and the proportional to temperature. And this is called Mott formula for thermopower. What happens, the interesting aspect here is that these derivative of conductance as a function of energy can be split into two parts. One is dG over dN. By the way, this derivative also makes it extremely sensitive to the density of states or any kind of low energy structure in the density of states. Okay, so this part, this 1 over G dG dN, is experimentally obtained directly because most of our devices, you make measurement of the transport character or transfer characteristics where conductance is varied as a function of density. So you can directly get this number from experiments. And this one is essentially the density of states or electronic dispersion. Okay? And that helps because now you can actually look at the nature of the density of states, which gives you a complementary information about the electronic properties in complementary to other transport or thermodynamic probes. Okay, this is diffusion thermopower. However, if you've got phonons, and this is called phonon drag, that because you're creating, when you create a temperature difference in the system, in addition to electrons, even the phonons will move. So they drag the electrons along with the phonons, and that leads to a drag or phonon drag thermopower. The phonon drag thermopower essentially depends upon how the electron phonon coupling of the system is, and also how many phonons do you have, and hence the number, this Bose-Einstein distribution, that's essentially occupation probability of phonons at a particular value of energy and momentum. Okay? So if you look at the Mott thermopower, it doesn't take into account the phonon drag part. So if there is a violation of the Mott formula, which is what this talk is going to be, looking at the violation of Mott formula, it can come from either the phonon drag component, or if there is additional component that the semi-classical Boltzmann equation does not consider, for example, an electron-electron interaction and so on and so forth. Okay. So I'm going to give you a very brief example of how the Mott formula is sensitive to the density of states of a two-dimensional system. And for that, I took an example of the bilayer graphene. So the way we do the experiment, we have a bilayer graphene and you pass a current, and which is a heating current, which sets up a temperature gradient across the length of the sample. And then you measure the voltage which is developed in these two contacts, and that what you call the thermal voltage. Okay. To give you an example, you see the resistance of this system, which is a standard 4-probe resistance, is like a standard bell-shaped curve. But if you measure the thermal voltage, which looks like something like a derivative of the resistance versus gate voltage itself. Gate voltage is nothing but the density, okay, or proportional to the density. Now, this leads to this kind of a Mott formula verification. 1 over dG dN comes from this experimental form, and dN dE is nothing but the density of states of bilayer graphene, which is a standard parabolic band structure, which is constant. And if I take a product of these two, you can see, you can explain the experimentally observed thermopower quite nicely. The thermopower is the sensitivity of the thermopower to the density of states can be seen from this data. You can see this was for bilayer graphene sample. If I use the bilayer density of states, you can see the green one explains the data quite nicely. But instead of bilayer, if you instead of take single layer graphene band structure, you cannot explain the experimentally observed thermopower anymore. Okay. Now, Aditya did some really neat experiments on understanding what happens with in thermoelectricity and gap bilayer graphene, and this is where the sensitivity of thermoelectricity to underlying electronic structure can be illustrated. For example, if you take bilayer graphene and you put two gates across its two sides, then you can open a band gap. And when you open a band gap, you can open a large band gap. For example, you can this particular R versus gate voltage graph is at a gap of 0.5, whereas at this point it was just zero band gap. So at zero band gap, the resistance was much smaller. At large band gap, the resistance at Dirac point or then charge neutrality point is much larger. So that's it. All you do is you create an electric field across the bilayer graphene, open a band gap. What happens if you now do the thermoelectric power experiments? The previous graphs that I showed you were all carried out at zero gap. Now, if I do the same experiment at finite gap between the two, conduction and the valence band, you can see there are some interesting features that come up which cannot be purely explained by an apparent derivative of R versus gate voltage. For example, you see these regions become skewed, or there is an additional shoulder that develops. But you see the resistance versus gate voltage features nothing in that direction. So you will not be able to get this from simple derivation of R versus VG. And this is this problem has been solved by Aditya. Hopefully we'll get the paper out very soon. He says that this is an effect of the change in the density of states because of the skew scattering or the trigonal warping behavior, which leads to a Lifshitz transition in the bilayer graphene. This essentially comes because in addition to the nearest neighbor interaction between the two layers, the next nearest neighbor interaction of gamma 3 usually leads to a Van Hoff singularity in the density of states. And this density of states is, this is without the Van Hoff singularity, which is nothing but flat density of states. But if you have got this additional coupling between the upper and lower layer, you have this Van Hoff singularity that gives you another a singularity. And that leads to, he did the full calculation by taking into account additional component from strain, and you can see the shoulders now develop. So it means that Mott formula is not really violated, but the density of states was non-trivial because of the observation of the Lifshitz transition from the additional skew coupling component. Okay. This is an example. I'm going to now go to the first question of today, is that what happens in the cross-plane direction? That means when you have two graphene layers which are sufficiently widely misoriented by about 12 to 13 degrees, if you want to know what is the nature of coupling between the two layers, then you would like to measure the thermoelectric power between the two layers by heating one layer, but measuring the two layers voltage that developed between the two layers. Okay, this is the overall schematic. I'm hoping this is fairly clear. You take two layers, you pass a current in one of the layers and measure the voltage between upper and lower layer. This is a device geometry. What we normally do in the lab, this is what we started with. Recently, we have changed the protocol. I'm going to say that a little later. We take one layer of graphene and then we rotate it by an angle. If our intended misorientation angle is theta, we would rotate it by 60 extra degrees like this, so that the effective misorientation angle remains theta, but we can now have the electrically, you can access all the upper and lower layers as we wish. Okay, so we can pass a current here and measure the voltage here. And then we we put a gate on top like this, and then change the carrier density in this overlap region between the upper and lower layer. This is how a typical device looks like, and this is usually covered from both sides by boron nitride, because boron nitride gives you an extremely clean and lattice matched environment to graphene. As a result, it's usually a very high mobility system and clean system that we can measure. So if you understand the interesting reason why we started this whole exercise altogether, is simply asking the question, what happens to thermoelectric power when your thermoelectric material is squeezed to just interatomic distances? Because the van der Waals distance between the two graphene layers is 0.3, 0.4 nanometer. So we are talking about thermoelectric voltage generation really at a distance which is half a nanometer or even less. Okay? So that was the interesting question that we started this whole work with. Now then what happened is, you can look at the electrical transport first. You can see in this case, you can pass a current from lower layer to upper layer, and you measure the voltage between the two layers. And essentially this is a standard by bell-shaped curve, means that when the overlap region is charge neutral, resistance is high. When you dope it with electron and hole, resistance falls down. Okay. However, if you do the experiment the thermoelectric way, that means you pass a current in the upper layer and measure the voltage between the two upper and lower layer, you will see that naively it's like a derivative of this graph. You can see as you increase the current between the upper layer, you'll see that the voltage difference between the two layers starts increasing quite heavily. And then you can divide to make sure that it is nothing but a thermoelectric component or thermal component. You divide the voltage developed by the square of the heating current, because it's directly proportional to the power. Then you see that all the traces have nicely collapsed. And also by using the resistance of the upper layer and lower layer, you can measure the temperature, delta T, which is the difference between the upper and the lower layer. Okay. What is interesting, and I want you to take a note of this, that by increasing the heating current, we can see the temperature difference between the two layers is increasing, and you can actually maintain a temperature difference of nearly 30 Kelvin or even more, 30 to 40 Kelvin between two layers of graphene that are separated by 0.5 nanometer, and which is actually staggeringly large temperature if you think about it, between two systems which are so close physically. So which actually is a very interesting observation in itself. Now, if I want to look at whether the Mott formula is violated or valid in this kind of a behavior, I have calculated, we have both the electrical transport and the thermoelectric transport. And you can see that this is, the red ones are calculated from the equation of, this dg, G is obtained from the experimental transfer characteristics, and dNdE is essentially the singular density of states because they are decoupled. You can see the Mott formula does not at all explain the experimental observation. Instead, what we see is actually a very different temperature dependent behavior. You can see that normally if you come up with a diffusion thermal power, it is supposed to be proportional to temperature. But at all gate voltages, each question. Yeah, sure, please.
Yeah, if you go to the last slide, how do you distinguish between whether this delta T? Sorry, the last another slide back actually.
Yeah.
So regarding the delta T, so how do you distinguish between whether it is the delta T between the two graphene layers or it is the delta T in plane delta T, for let's say for the same plate at the same plate. So how do you distinguish that?
Right. So okay, it's a very interesting question. Normally, what we do is that we measure the 4-probe resistance of the graphene, two graphene layers, to measure its temperature. Why I believe it is unlikely to be the temperature difference within the same graphene layer is because within the same layer, the thermal conductivity of graphene is extremely large, nearly 5,000 watt per meter per centimeter per Kelvin. Okay, so it's extremely hard to retain a temperature difference of such a large number within an individual, within a single layer. Okay, so I doubt it is temperature difference within the layer, but we measure the two temperatures independently from by measuring the 4-probe resistance of individual layers. We measure at different points of the graphene. So I'm guessing that if it had been a difference within the layer, it would have come out if you measure at different points of graphene, which is not the case. I hope that answers the question.
I got your point, yeah.
Okay.
Thanks.
Sir, I have a question. Can I ask?
Sure, please go ahead.
So here in this plot, you have shown just the change in delta T is up to 30-40 Kelvin. And in the next slide, you have shown a data at 20 Kelvin. So usually it is this mod formula is only valid if the delta T is much smaller than the this average.
Absolutely correct. Yes,
So,
you're absolutely right. So you're very nice question. It's absolutely right. And what we normally do is that while we show that the delta T can be as high as 30 Kelvin, it was essentially needed to see how delta T varies with the current, because we want to check, whether it is square of the current and so on and so forth. But actual measurement was done at, say, 1 microampere or so. And so the temperature scale, if you can see, it goes from room temperature to about 20 K is what I'm going to show you. So the delta T is always much smaller than the actual temperature itself. Is that okay?
Yeah, sure.
Yeah, good. No, that's a very important point. Okay, so then I'm going to go here, and what I showed here is that, you see, this is the saturation of thermopower at every gate voltage rather than a linear increase. And so it clearly is not a diffusion thermopower. It's a violation of the Mott formula has come. And we found that this is essentially a phonon drag effect. The idea here is that if upper layer is hot and the lower layer is cold, then by having this larger number of, the higher number of phonons here, they kick the electrons out, and hence they create a charge imbalance or a difference in chemical potential. And it's a very easy, just a back of the envelope calculation, where you can show that S then is nothing but derivative of the phonon occupation number itself. And all these lines that you see here is nothing but this equation that is fitted with just one parameter. Well, I mean, two parameters, because we have the energy coming out as well. Okay, so this is nothing but the derivative of the density of states of the phonons. To verify which phonons, actually you see this energy can be plotted as a function of density, because the density is what is varied. And this is where you can see the energy is when you extrapolate the energy to the zero, the center of the Brenner zone, you see the density is nothing but the energy of the phonons is 100 K, which is precisely what the energy is for the ZO modes, or the outer plane breathing modes. Which is very nice, because we now have a nice picture that by creating a temperature difference between the upper and lower layer, you are actually creating the electron phonon interaction, or the phonon drag essentially at the 0.3 nanometer scale, is leading to the thermopower, which is governing the thermoelectricity in twisted bilayer graphene when the misorientation angle is very large. What happens when misorientation angle becomes small? And this is where you can see the electrical transport between the two layers become very different. First up, so this is at 12 degrees, and you can see a quasi-insulating type of behavior. You can see this conductance increases with increasing temperature, but at low temperature it saturates. Whereas in the case of very low misorientation angle, the conductance is relatively weakly dependent on temperature itself. So I will show you what happens in the case of 2 degrees when the misorientation angle goes down to about 2 degrees. Now we are recovering the Mott formula. Okay, you can see that this is at 85 Kelvin, at 150 Kelvin, and 300 Kelvin. These lines are calculated from the electrical transport, and you can see the Mott formula relatively satisfactory, or at least much better in estimating the experimentally observed thermoelectricity. In addition, if I now plot the thermoelectric power as a function of temperature, you can see now the linearity of thermopower with T is now recovered. So what we have done is that we measured these at large number of devices and categorized them. What we find, and this is the summary of this part of the study, is when you have angle between the two graphene layers larger than roughly 5 degrees, you see this saturation as a function of temperature, whereas when the angle is smaller than around 5 degrees, you recover the Mott formula and there's a linearity of the thermal power. We can understand this as well, and this is what recently come out. The basic idea can be taken from an old calculation of McDonald, Alan McDonald in 2010, which essentially calculates the hopping probability or tunneling rate between the two layers, simply taking the graphene layers as a RC circuit, okay, and looking at its density of states, and you can calculate the hopping rate of electrons from one layer to the other. And you can see that if you take the phonon frequency, which is somewhere around 10 to the power of 12 here, at an angle of about 5-6 degrees or so, the phonon frequency and the electron hopping rate becomes similar. So it means essentially that when the angle between the two layers is smaller than 5 degrees, then the hopping rate is larger, and it's the electron hopping that becomes more efficient to make the electrons go from one layer to the other. And the standard Landau-Buttiger formula to the diffusion thermal power, Mott formula, is good enough to explain the thermoelectricity. Whereas if the thermal power if the angle between two layers is larger than about 5-6 degrees, now the phonon frequency has become larger, and it is the electron phonon coupling that causes the thermoelectric power to generate as through a drag kind, which I have explained to you earlier. A very quick slide for those who are applied oriented. You see there is a very interesting question about what will be the thermoelectric figure of merit of such kind of a system. It requires a measurement of thermal conductivity, and we are doing that right now. And it's quite, one of the excitement in this is that because you can engineer which phonons you would like to keep and which phonons you can eliminate from your thermal transport, you actually can, in principle, get a very high ZT factor. That's what we're looking for. In principle, this could be, a very competitive thermoelectric system at high temperatures. Okay, but this is
I have a quick question.
Yeah, sure, please.
So is there something special that happens at 1.1 degrees, although you're at higher temperatures?
Okay. Sorry, the question is at 1.1 degree or high temperature. Can you repeat the question?
No, at 1.1 degree, but I see the temperature scales of your measurements are all 40, 95, and so on. So,
Correct. So far, I have only showed you. I have not shown 1.1 degrees. I've primarily showed. If you look at these numbers,
yes.
0 degree, 2 degrees, 4 degree, and these are large degrees. So far the interest has been confined to high temperatures because I wanted to understand the coupling between two layers, and we will now go to the interesting part of close to magic angle.
Okay.
So I have one more question actually.
Sure.
So what will be the effect of like the phonons of the substrate? Will they have any effect in your observation?
I'm sorry, your voice was slightly garbled. Can you tell me again?
What would be the effect of the substrate? Like if you, let's say, instead of using H plane, if you use that SiO2 substrate, so will the observation change and sense? That's my question.
So all our experiments have been done on boron nitride substrates, but so we do not really know. In sometimes if there's a graphene and boron nitride layers align by accident, there could be some effect, but unfortunately I don't know whether such a thing has happened. So I can't really give you a very quantitative answer. All I can say is that everything here is encapsulated by boron nitride, so it's a highly mobile system. So so the substrate probably at this point of time can be ignored. At least we cannot. Okay, Karthik, how am I doing with time? Can you just give me because I don't have any.
So you have another 20 minutes. That's 1 hour. So another 20 minutes you have to finish up.
I'll finish in 15 minutes. Okay, fine, good, 15 to 20 minutes. Good. So now I'm coming to the question of what happened. Now we will slowly do step by step. and we'll go to closer to magic angle. And now you see what we have shown here, that when you have angles which are less than 5 degrees or so, it's 2 layers start hybridizing. And once they start hybridizing, the electronic bands gets modified. And one of the questions that we asked here is that, okay, if I don't go all the way to magic angle, partially because getting magic angle is not very easy experimentally, it requires several samples. So we had this one, which is about 1.6 degrees, which is not superconducting, but it is fairly low, where electron correlation effects could, in principle, could manifest. So we asked the question, okay, can we measure thermoelectric property? Now this is in this experiment, the goal is to measure the in-plane thermoelectric power, because our goal here is not to see with the coupling between 2 layers, but essentially if there is a new electronic phenomenon that is occurring within the overlap region. Okay, so apart from this way of 60 degree additional angle, we also make samples using this tear and stack method, which is coming from the MIT group, and now students here can do this quite regularly. For example, if you see, you take, this is the full graphene layer. If this is the full graphene layer, you use a boron nitride here to cut it, and then you take it on top of this and give it a small twist. So you can see this part has been cut and taken all the way here and given a tiny twist of whatever angle you want and put it on top. So you know, since the original graphene has come from the same, or the 2 parts come from the same original graphene, you know the angle exactly, and it is much easier to get the angle you desire within some error bar. So we make these samples. The way we create these samples, the typical devices look like this. We always make in such a way that a single layer part is protruding out of the twisted bilayer region. So this is a twisted bilayer region, and this is a single layer graphene region. And the goal here is simply that this is our sample and this is the heater. Okay, so we pass a large heating current here, so single layer, and create a temperature difference between the across the length, and you can measure this. So this is an additional device geometry that we have started working on recently. So basic idea here is that if you can see this is the calculation done by Shinjan and Manish in my department, and if you look at the overall density of states, this is the low energy bands, and this is the first Moira band, and this is the second one, and third and opposite ones here. So you can see the density of states go to 0 at this point as well as at these 2 points, and as a result you get high resistances at these points. And you can see that this is indeed the case. You, as a function of gate voltage, as the Fermi energy is swept across these energy, you get 3 peaks. And these 3 peaks correspond to the full filling of the Moira band. And this is the charge neutrality point. And this is also a fulfilling of the Moira band from the valence band side. Okay. So what's interesting here is the temperature difference. You remember, I mean, in a standard magic angle device where the misorientation angle is 1.1 or so, then there is a strong peak, which I'm going to show you later, even at half filling. But in 1.6 degrees, where the correlation effects are supposed to be weak or non-existent, we do not know, there is no additional peak here. But if you look at the temperature difference, dependence, it's essentially linear with temperature. This is, you can see this inset where the temperature versus resistance versus temperature is shown. You can see a very linear temperature dependence at various density points here. But if I take this new half, that means half filling. By the way, when I say nu equal to 2, it essentially means half filling, which means essentially nu equal to 4 is full filling of the band, because there are 4 different bands which get filled up. But nu equal to 2 corresponds to half filling of the Moira lattice, either from the electronic doping or the hole doping side. In both cases, you can see that the resistance versus temperature is amazingly linear with temperature. Okay. Now, the reason this is, okay, I mean, and this remains so for, we have another sample, which I'm going to show you later at 1.24 degrees. You can see the linearity is maintained, and there's a 1.7 degree sample, which has got a very similar slope, rho versus t, and, but the linearity is maintained as usual. The reason this linearity is very interesting and it led to significant controversy is because whether it is some form of manifestation of a non-Fermi liquid behavior, or whether the twisted bilayer graphene is after all a strange metal. And this kind of thought has been discussed in context of the similarity between the twisted bilayer graphene superconductivity and high TC superconductivity. Whereas you can see that this was a PRL earlier this year, in which the correlated when in the superconducting regime just over here, when you do a temperature dependence of resistance, there's a very strong linear temperature dependence, which is observed even in bulk high DC superconductors as well. So, question that we asked here: okay, is there a correlation effect in our system at half filling, where the resistance is after all linear with temperature? So for doing that, we looked at the thermoelectric power. Okay, so this is the 3 peaks in resistance that we saw, and this is the measurement of the thermal voltage as a function of the thermal voltage as a function of gate voltage or the density. Okay, and you need to look at the derivatives here. So you can see if its Mott formula is valid, then everywhere where there is a flattening of the resistance versus gate voltage, the thermoelectric voltage should go through 0, because it's whatever the density of states is, it doesn't matter, because proportionality to dr dVg is always there. So everywhere there is a derivative which is of resistance going to 0, the thermal voltage should go to 0 as well. So you can see that there is a 0 here and there's a 0 here, which means that, okay, it's probably can be considered as Mott formula. But as you cool things down, so this was at 60 degrees, this is at 35 degrees, this is at 20 degrees and 10 degrees. Now you can see there's a stark difference coming up. So this point where the thermoelectric voltage is supposed to be 0, you can see an additional component which is negative in the electron dope side, and hole dope side, and positive in the electron dope side. It's essentially, you can take the charge convention of negative minus E. Okay, so and this is of course down to 3 Kelvin. This whole thing remains. If I now take the density of states calculation from Manish and Shinjan's calculation, you can see something really interesting. This is the density from the density of states of theta equal to 1.6. You can plot this Mott expectation, but you can obviously will not get a Mott formula to be obeyed, where exactly at the plus and minus half. Now, I have shown this as a function of temperature in this figure. You can see the at half filling, there is a negative excess thermal power, and at half filling on the other side, there's a negative, positive excess thermal power. And these are different angles. You can see at 1.6 and 1.7 degrees, they do have very similar. 1.7 is already going down significantly. At 4 degrees, which is significantly large misorientation, this excess thermal power essentially vanishes. Now, what's so interesting about this additional thermal power is that if I look at its temperature dependence, please take a look at this inset over here at minus and plus half filling. Is this thermal power does not go down to 0 as the temperature is decreased, which is very interesting, because thermal power is essentially entropy per unit charge in a system. And one expects, according to the second law, third law of thermodynamics, that you would expect entropy to go to 0 as your temperature goes to 0, unless there is a completely new different phase. There are different suggestions. One of the suggestions is whether there is a Planckian dissipation that goes on. There is a similarity of thermal power of the physics of bilayer graphene with that in various high TC compounds. And what we did is we looked at the possibility of Planckian dissipation. The Planckian dissipation is nothing but from the d rho by dt, essentially, you calculate the scattering rate. And this scattering rate is nothing but if I look at the scattering rate as normalize it with respect to the 2 pi kBt over h cross, then whether it is in the order of 1. So it does look like something similar, which led to a lot of controversy. I don't want to go into detail here because we still don't understand what's going on, but these are experimental data, which looks very, very interesting and intriguing. We've tried to understand if there is a new phase which is developing here, which is what kind of new phase, probably where the excess entropy coming into play. We applied a lot of magnetic field at 3 Kelvin, and we found that the magnetic field has hardly any effect. And as a result, our current understanding is that it's an orbital entropies through probably some form of valley polarization effect that is giving rise to this excess entropy. We don't know, but there are also very recent experimental papers on Pomeranchuk effect, which essentially shows that at low temperature, the isospin or the valley isospin polarization gives to a liquid state, and that can give to finite entropy at low temperatures. So maybe something of that sort of will be happening, but we are not sure at this stage. Question is what happens to go even farther to lower and lower angle, and this is a very recent experimental data which is at theta of 1.25 degrees, and now you can see Mott formula is violated everywhere. It's just you can see now additional peaks at these are at half filling roughly. The peaks have started emerging, and this is the calculation from the Mott this line, and these are the experimental data, the inside lines. And you can see that take the difference. Every time there's an insulating behavior, there is a strong Mott formula. So it sort of tells us that there is something really a lot of things happening in terms of electronically as you go to lower and lower angle or closer and closer to the magic angle. These temperatures are very low, 280 millikelvin, this is 730 millikelvin and 4.5 Kelvin. Remember something very important here. We are measuring thermoelectric power, which means that we need to create a temperature difference. And the question, which was very nice in the beginning of the seminar, that the temperature of the sample must be much larger than the temperature difference you use to measure the thermal voltage. So you need to create a much, much smaller temperature difference, which means the signal is extremely small in many of these measurements. Okay. So I just wanted to flash this. We just have to, we are just going to show this and say that, okay, this is what is happening. There are these insulating regimes which are Mott formula violation is maximum. So probably these are some form of broken symmetry phases, and everywhere there is an insulating regime comes through, the phases are, the Mott formula is no longer anywhere near in the picture. Okay. I'm primarily done. Karthik, can I have 5 more minutes or something?
Yeah, I think 5
I have one question.
Sure, please.
Yeah, so regarding this Mott formula, whatever you have generated, this S you have generated that I can see in this figure, in the second figure, this is the order of magnitude as it is very close to the bilayer Seebeck what you have shown earlier, theoretically calculated, I mean. Okay,
so for example, the calculation, yeah, I mean, in terms of the pure number, it is similar in the tens of microvolts.
Yeah, so there I have one question, because like density of state, that factor is also there in the Mott formula. That is almost 1,000 times higher for like close to magic angle. If you go, it is almost 1,000 times higher. How is it giving theoretically the same values in S?
Okay, first of all, theoretically, this has not been calculated what the number is. The density of states are calculated theoretically, and then what we can do is that we take the transport that is 1 over g dg dn experimentally. We multiply the theoretically calculated density of states, and then we scale this number to match the experimental number. Yeah.
Okay. Okay. So the scaling is also there. Okay. Okay. Got it. Okay. Thank you.
Okay. All right. Okay, so I wanted to finish something here with, a completely different direction. And this is also something which is becoming quite interesting now. And this is something called okay, let me just, yeah. This is what is happening in the minimally twisted bilayer graphene. So other than the magic angle by twisted bilayer graphene, and where the angle needs to be extremely close to 1 degree or 1.1 degree, where the correlation effect becomes stronger, and then a lot of things are happening. The new broken symmetry phases are emerging. There's another regime where the bilayer graphene twisted bilayer graphene, when the angle of mismatch is extremely small, something around 0.1, 0.2 degrees, you get a very different kind of structure, because what happens now is the reconstruction of the two lattices gives rise to moire bands, which look something like this. This is a TEM image from the Harvard group. And you can see that now you have essentially got these moires where these are of different Chern number, the opposite Chern numbers. And hence, these lines essentially form what you call a topologically protected linear set of network. Okay, so current can flow without resistance along these lines. As a result, in this paper, you will see that there are quantized conductances emerging in this minimally twisted bilayer graphene. And there has been very interesting work. I mean, this is the work from Manchester group. When you apply an electric field between this and you open a gap, so you confine your current flow only along the lines, you get Arindam effect, which essentially is oscillation in magnetic field. Or STM experiments also show this kind of a triangular reconstruction of the electronic bands. Okay, so there are very interesting direction or a topology at minimally twisted bilayer graphene. So we wanted to, I mean, again, this is a device which came accidentally, but this is another device where the angle was created or was found to be very small, and that was and there was a small displacement field also created. Anyway, so if I look at this, what is interesting here is if I take a look at this resistance versus gate voltage, it is a standard resistance bell-shaped curve. And if I do a magnetic field versus gate voltage, you can see these Landau levels are emerging through a fan diagram. And from the two here, that is the difference between the two sets of Landau levels, you can get what is the moire lattice size. And from the size of the moire lattice, you can get what the twist angle is, and we get a twist angle of roughly about 0.16 degrees or something of that sort, which leads to a moire lattice of this kind of moire lattice of about 90 nanometer or so. Okay. So that's one can immediately calculate. What's interesting about it is that instead of standard electrical measurements, which essentially is featureless kind of, and these are done at nearly zero displacement field. If you do a thermoelectric voltage, that thermoelectric measurements, where you pass a current here, now measure a temperature difference here, you will start seeing that in addition, this very nice structures starts emerging. And these are essentially oscillations in the thermopower. So what you do here is you take at a particular gate voltage, say the zero gate voltage, and you look at the magnetic field dependence of the magnetothermopower, and you'll see these beautiful oscillations. Okay? So now what is interesting here is that these oscillations actually correspond exactly, this delta B of 240 millitesla corresponds exactly to the moire lattice size of about 90 to 100 nanometer that we get from our calculations. Even more interestingly, if I look at the resistance in the same regime, you can see the resistance shows nothing essentially. And this sort of led us to conjecture that thermoelectric power probably is a much more sensitive probe to any kind of low energy phenomena in such systems. And we still, we're debating what the reason could be, that why thermoelectricity picks up these Arindam oscillations, which can come from the topologically protected channels, whereas resistance is unable to do so. there could be possibility that the thermoelectricity is proportional to the derivative of the density of states, and hence it is more sensitive. Or it could be a possibility that it is in a quasi-thermal equilibrium all the time, and hence it is more sensitive. We do not know that, but it's an experiment which I think is quite interesting. So with that I'm going to finish. And so this experiment is essentially a brand new experiment. We haven't even started writing it up, but hopefully we will do so very soon. So these are my summaries. I just showed what happens at how the coupling two layers can be probed using thermoelectricity within two cross layers. And then we showed how a phonon limited coupling becomes electronic coupling at a lower angle, again directly evidenced by the change in behavior in thermoelectricity. Again, the thermoelectricity was found to be weakly sensitive to weak low energy features. For example, the left shift transition that Aditya saw in bilayer graphene. And also, as you go close to the magic angle, it becomes sensitive to the emergent phases. Okay, but well, with that, I would like to stop here. If there's any question, I'll be happy to take.
Thanks, Arindam. You're spot on time. So I think now the floor is open for questions. So anyone who has questions, please go ahead.
So again, I have one more question. So it's from the first part of your talk. So why do you measure the?
Some of the voice is becoming indistinct. Can you just speak?
Yeah, louder? It is louder.
Sir, I have a question from the first part of the talk. So
yeah, sure. Please go ahead.
You showed a curve where you have plotted delta T, cross plane delta T with temperature or something. So how do you actually determine the delta T between the two graphene layers?
Sure. Okay. So in most cases, when the cross plane thermopower was done, the delta T was measured by looking at the two graphene layers, the resistance of two graphene layers at the heating angle for heating current. So what you do is we first do the temperature dependence of resistance of the graphene layers. So you know at what temperature what the resistance is, and then you pass a current through that, the heating current, and you look at the change in resistance. And from there, you actually know from what heating current, what is the temperature. So we essentially use the resistance of the individual graphene layers as the thermometer.
I see. Okay. Yeah. Thanks. Yes.
Yeah.
Yeah, so Saurabh had a question. I'll ask a question, and then maybe you can ask subsequently if that's fine.
Okay,
so
can I ask a question?
Yeah, Saurabh.
Okay, so in the low angle twisted bilayer graphene data, sir, even near the primary Dirac point, the main Dirac point, as well as near the band insulating region, it seems that the Mott formula is not valid.
Right.
An effect will not be there at the primary Dirac point as well as the band insulator, right? So why the Mott formula is violating near the primary Dirac point as well as near the band insulating?
Actually, no. Okay, it's a good question, but it is not true that near the primary Dirac point it is not valid. If you take a look at this region,
yes.
Okay, this is the region which I would consider the Mott formula is valid. Of course, one can also ask the question whether the inhomogeneities near the primary Dirac point can lead to some form of a discrepancy. Probably it is. But overall, actually, you can see that the Mott formula is relatively well satisfied near the primary Dirac point. It is in these regimes there is absolutely no Mott formula where it is. Yeah. So I think your question was, I mean, I say that in the Mott formula is approximately valid, at least, or to a certain extent, I'm happy with Mott formula, close to the primary.
Yeah, close to, but near the band region, band insulating region, it's small.
Oh, near the band insulating region. So the band insulating region falls just outside this over here, and there the thermopower essentially becomes erratic. It fluctuates massively, which is why we eliminated that. Our goal was to see the electronic phases within the Moire band. So, and when the band insulating region goes essentially this is like a hard gap. And in the hard gap, the derivative of the thermopower means is nothing. It doesn't have any significance. So at that region, thermopower is essentially fluctuates, like which is impossible to. It's essentially meaningless measurement over there. So everywhere here, it is within the band insulating. It is outside the band insulating region. This is within the Moire bands.
Okay. And my second question is related to the first part. In the gap bilayer graphene, you showed the some signature of the Lipschitz transition with the help of this thermopower. So what was the charge inhomogeneity in that device? Because it will highly depend on the.
Yeah, that's a great question. Right. So actually, I didn't mention that, and I should have. But anyway, I think it's too far. So that was observed in a bilayer graphene, which is extremely high mobility. Aditya will be able to tell exactly number. I think it's more than 100,000 mobility, or 90 to 100,000 mobility, or something of that sort. So it is good enough mobility. At least you are absolutely right that if you do not have high mobility bilayer graphene, you will not be able to see the Lipschitz transition because it's going to get smeared. So it's only when he could obtain a high mobility bilayer graphene, and other graphene devices did not show this. So bilayer graphene, it's only the high mobility bilayer graphene where the the trigonal warping could be observed. He could see the shoulder.
Okay, thanks.
Yeah.
Yeah. So go ahead. Anyone else? Yeah.
Can I ask?
Yeah. Satya had a question, right? Yeah.
So thank you first of all, thank you for exciting talk. So my question is, what material did you use for gating?
For gating, so these are essentially standard. We take graphene within encapsulated boron nitride layers, and then use a chrome gold deposition to create a top gate, and the bottom gate is usually the global silicon oxide.
Oh, chrome gold bilayer. So my question was there for the last part of your talk on the origin of magnetoresistance measurement.
Okay.
So is there any contribution from chrome?
The last one was I don't know which one, but maybe this one or the one.
Magnetoresistance, last part.
Okay, you mean this one, or no? Sorry. Okay, no. I mean, let me answer the question anyway. This is magnetoresistance in some form. But,
okay.
So the chrome gold is essentially on the gate. Okay.
Yes.
So, and this chrome is not magnetic in nature, and we normally use this chrome gold for a large number of devices, and at the thickness level at which we normally do these depositions with the chromium is in the order of 5 nanometer, and gold on top of this. First of all, there's no visible magnetism in the chrome gold layer that can affect the magnetoresistance in the sample. Because you can also check this using Hall measurements, and we have done it. So Hall measurement shows no effect of gold chrome layer on top.
Okay, thank you.
Yeah, I have one question.
Right, go ahead.
Yeah, for the smallest angle device, do you have any in-plane magnetic field? In-plane magnetic field, this Seebeck data also there? This oscillation is there.
Good question. As far as I know, we have not done any in-plane. I mean, the in-plane magnetic field data might have been taken. I'm not sure. I can't say very clearly at this point. But this is, of course, of perpendicular field data. The other data where I showed magnetothermopower, it was in-plane magnetic field, because we wanted to look at only the spin effect. In this case, there is no in-plane field.
Okay, thank you.
Hi, I have a question.
Sure, go ahead.
Very nice talk.
Thank you.
Explain the origin of this finite entropy at zero temperature that you were talking about, and what could possibly be the mechanism for that?
Right. So that is a question which I don't have the answer of. So first of all, this this region is critical, and this is very interesting. We have been able to go down to 10 Kelvin or 5 Kelvin in which the entropy is there. There are theories which are originally developed through this the Bekenstein black hole kind of entropy, which might be having some relevance to the high TC superconductors because of the quasi particle. There is the lack of quasi particle in that because of strong interaction has been shown that it could lead to some form of zero temperature entropy. Now, whether that is relevant to this at all or not is far more controversial a point than what we can discuss here. As far as we are concerned, we are measuring the temperature. There's temperature dependence of entropy, which seems to not going down to zero, whereas thermodynamics wants us.
I was thinking more along the lines of, for example, spin liquid behavior, some sort of frustration.
Absolutely. Yeah. I mean, take whatever basic platform you want, but only problem here, the real spin would probably be destroyed by a magnetic field. And if you look at this particular data, this is the data in which magnetic field was created in parallel. And you can see the excess entropy part, which is this part and this part, is not affected by magnetic fields up to 9 Tesla. As a result, we are kind of skeptical whether real spin can have an effect. However, if you think about the Valley isospin and then start thinking from an orbital point of view, there might be some interesting questions there.
I see. Thanks. I see. It's very interesting. Thank you.
Thank you.
Okay, so I think in the interest of time, we will end today's session. So on behalf of all the participants, I think I will again thank Arindam for such an enlightening talk. I think with this, we are done for today's session. I thank everyone for attending today's talk, and we look forward to the next session, which is a special session again next week by Professor Fabian. This is on December 22nd, I guess. So it's close to Christmas, but I think I hope that many people could join in and participate in this next session. So with this, I think I thank you.